Now if you run your code and you're worried about the smoothness of the trajectory, keep in mind that we used only 25 particles. So if you don't like that, modify this number, which is set in the main function. So here is a result which I obtained using 200 particles. So as you can see, the trajectory is now much smoother and looks much more like the desired result. So in the beginning, all the particles are the same, but shortly after, the 200 particles spread out nicely. And we can see the typical effect in the left turn, where some particles take a stronger left turn. Even though we have more particles, we still have the effect that this landmark is dropped since it is not observed, as it is occluded by this landmark. Shortly after, this is inserted again. And we also see, of course, spurious landmarks in other places. They usually disappear shortly after they are introduced. So this is our final FastSlam result of this unit. So let me make two additional remarks with regard to the efficiency of FastSlam. The first is about the proposal distribution, and here the problem of the presented FastSlam approach is that our proposal is made only based on the given control. And this may lead to inefficiencies, because if our control is very noisy, this may lead to a wide spread of particles, out of which only a few will survive in the end, because all the others do not fit very well to the measurements of our robot. And so in the approach which was presented here, we do not care about this. And in the book of Thrun, Borgard and Fox, this is also called FastSlam 1.0, and you'll find a different solution called FastSlam 2.0 in the book, which modifies the proposal distribution so that the measurements are taken into account. And the second remark is with respect to map management. Now you have seen we take m particles and say we have up to n map features or landmarks. And if you now check with our implementation, you will notice our time complexity is in the order of m times n. For example, in resampling, you will find a copy function which copies an entire particle, including its map, in case the particle is picked. Now let's have a closer look at this. So we have our particles, where each holds its own position, and also the estimated position and covariance of every landmark. In our resampling step, whenever we pick one of the particles, we copy it. So we may have two or more identical copies of the same particle. And so overall, since in resampling we have to pick a total of m new particles, and each particle requires copying all n variables of our map, our implementation is indeed in the order of m times n. Now let's see what happens to our two identical copies of landmarks here. First of all, during the prediction step, they will move differently, which will not affect the map. And then, when a measurement occurs, they will be updated differently. Now let's assume that this measurement relates to an existing landmark. So it will affect this mu k, sigma k of this particle, and it will also affect one filter, say ul, sigma l, of the other particle. Now if these particles are close, then probably k will equal l. So as you see, we will modify the list of landmarks only in one place, where all the other entries will stay the same. Now let's think about putting all the landmarks into a balanced tree. So mu1 and sigma1 would be stored in a leaf of a tree, as well as mu2, sigma2, and so on. And we would use a binary tree, and this would be un, sigma n. Now say this is our particle k, so we would put that into that tree, so we would have a pointer pointing to that tree, and whenever we need some element with a certain index, we would now have a logarithmic time complexity for accessing it. So far that's not an improvement. But now say during resampling, we pick this element twice, and instead of copying it, we'll just make a second pointer pointing to the root of the very same tree. Now what happens if we get our measurement C? Then, as we know, one of the elements will be updated, whereas all the rest stays the same. Now say our measurement would influence this filter of our particle L. So this needs to be modified, whereas all the remaining Kalman filters will stay the same. So instead of copying everything in order to just modify one element, we will do the following. We will set up a new root for our particle L, and since our element to be modified is here, we won't have to modify the right part of our tree, So we will keep a pointer to the unmodified right part, but we'll have to modify the left part. So we insert a new node here as well. But here the left subtree also stays the same, so we keep a pointer to the existing subtree, whereas the right subtree is modified. So we insert a new node. And then again, the left element is unmodified, whereas the right one is our new element. And so as you see, instead of copying all the elements, which will cost us in the order of n, we only have to modify those elements where you can see it's one modification per level of the tree. So it's only the path that we'll have to modify. And so instead of taking O of n, we now have on the order of the logarithm of n. And so our conclusion regarding the efficiency is that we can move from O of m times n to complexity of m log n, which is much better as the number of features in the map grows. So remember, that's the number of particles, and that is the number of map features or landmarks. There's another issue here, namely, if this is our particle, and if we get a new measurement, we have to find out the likelihood that this measurement corresponds to any of our features in the map. So in this case, we need to make sure that we don't have to compute the likelihood for all of our map features, but only for a small subset, so that picking the correct landmark in our list of landmarks does not take time linear in the number of landmarks. Now this is indeed possible, so that overall we get an asymptotic time complexity of m log n, which is a very good result. Now this brings us to the conclusions. So in this unit, you understood and programmed a particle filter version of SLAM, and I really congratulate you if you managed to program that, because even though the particle filter SLAM is conceptually not very hard to understand, it needs quite an amount of code to realize all the required functionality. Now in the particle filter SLAM, each particle is one path plus one map. So keep in mind, even though usually we only keep the last position and orientation of our robot, each particle stands for all the positions and orientation along the particle's path. Now one of the most important features was that our map features or landmarks are independent given the path, meaning of course the random variables describing the locations of our map features are independent when the path is given. And this has led to our solution to use one independent Kalman filter per feature, which has meant that in contrast to the extended Kalman filter SLAM approach, we have no correlations, and as you remember, those correlations were responsible for our covariance matrix, the size of 3 plus 2n times 3 plus 2n, which is quadratic in the number of landmarks. So while this is good, on the other hand, there's also drawback, since those dependencies are only implicitly captured by the FastSLAM algorithm in terms of the diversity of our particle set. The FastSLAM algorithm may not perform very well, especially with respect to loop closing, because due to particle deprivation, after a certain amount of time, the particles in our filter will have a common history, and so the dependencies that were captured through the diversity of the particles will be lost. If you're interested in this, please have a look at the probabilistic robotics book by Thrun, Bogart, and Fox. Now another big plus of FastSLAM is that each particle uses its own data associations, which is in contrast to other methods, for example, the extended Kalman filter SLAM. Here, we had to decide in each step the one and only data association. Whereas with our particle filter, each particle has its own individual data associations along the path. And this is a big plus, because this means that our FastSLAM algorithm not only samples across different continuous parameters, but it also samples across different discrete landmark associations. And finally, remember that the FastSLAM, amazingly, solves both problems, the offline and online SLAM, because each particle represents the entire path plus the map, so the set of particles represents the full posterior. On the other hand, we're usually not interested in the entire path, so we just keep the last position and orientation in each particle, and so we use the FastSLAM algorithm as a filter, and so this is the solution to the online SLAM problem. Now this concludes our unit about the FastSLAM algorithm. I hope you had as much fun as I did in implementing and running your very own FastSLAM algorithm.